Happy day today because I have Glenn back again. And Glenn has been thinking about the role of the observer in physics. And he thinks he's got a way to tie it all back into Chris Fields, Carl Friston, Michael Levin, Mark Solms, and we'll see why we've been talking to these people on the channel. So Glenn, take it away.
Okay.
I'm
Well,
at your disposal.
we haven't talked for quite a few weeks, maybe a couple months, but
That's right.
there's been a number of your episodes have sparked various threads, and they all kind of came together into one sort of conversation with you related to the observer in physics. And you also mentioned you had a special request at one point for a delayed choice quantum eraser from someone in the viewing audience. So I've had a lot of time for these ideas to percolate and mesh together and intertwine, and it's been fascinating, and kind of like to share it, get people's feedback. I'm not sure exactly what I've got my hands on. We'll see what the feedback is. So I think specifically, it began a while ago. You did a little solo performance where you were talking about collapsing the wave function, which is the Copenhagen interpretation. And I thought to myself, well, there's a lot more to the Copenhagen interpretation than just how you've presented it. You know, your approach is the consensus in physics. It's accepted metaphor. People know what you're talking about, but if you dig into the physics, there's a whole bunch more. In fact, I might say that if quantum mechanics is Alice in Wonderland, then the question of the observer is the rabbit hole that grants you entrance into that world. So if you hang on to that and we talk about that, I think it'll open the door into a lot of other things. Then when your talks with Wolfgang Smith, he was mentioning kind of obliquely in his own language that whatever the observer is in this universe, it can't be described quantum mechanically. So if you think quantum mechanics is the foundation of all of physics, and that the classical world we live in is just kind of a washed out big N a version of quantum mechanics, then you're sort of stuck, because if the observer is not quantum mechanics, can't be described quantum mechanically, then what is it and where is it? And that's one of the foundational questions that physics has yet to answer. I think another way to say it is physics as we have it now, the consensus concepts that you learn in school, is like an encyclopedia set, but it has a few volumes missing. And one of those volumes is the letter O for observer. And it's, people don't really want to tackle it. They don't know how to tackle it. But if you do, it opens a bunch of doors, and we'll go there and we'll see what people say. And the other thing that caught my attention was the meta-hard problem of consciousness and quantum babbling with Michael Levin, Carl Friston, and Chris Fields. And Chris has done some work with entanglement and the observer, how it relates to consciousness. I noticed when Michael Levin and Mark Solms were talking on your channel, they were getting very close to making that connection. So it's out there. There are more than one voice now in the realm of physics that has acknowledged that quantum mechanics can't describe the observer, and so the observer has to be something more. And then once you start asking that question, then you get into what, like I said, questions of consciousness, intelligence. And so that's where I'm going to try and take us today, and we'll see what happens. I have some pictures I have to show. I think, is it possible to share screen? Yeah. And then we'll take it from there.
Yes. So I gave you permission to share screen. So it
Share
should be at
screen.
the lower center of your screen. You should see a green thing that says share screen.
Okay, share. So I'm not seeing anything right now.
I can see it.
Oh, okay. Well, I did screenshots. Instead of showing videos, I thought we just did screenshots.
Yeah, so I see it. I don't know why you don't see it, but this is a screenshot of Michael Levin.
Right. So this is
Kurt.
from their talk, and it was like 2 hours, I think.
Mhm.
And they're just kind of, you're a fly in the wall in a coffee shop conversation. And if you're patient, they hit on some really good points in there. And I'm hoping by the end of our talk today, we might address some of the places they're going. So let's get back to the question of entanglement and the observer and observables. And we'll use this notion of entanglement and the paradoxes it generates as kind of a tool or a way to look at what the observer and what observables are, and kind of get an idea of what the observer must be and must not be. So let's try this. Now there's many interpretations for quantum mechanics, of which the Copenhagen one is the simplest and the one most commonly used. And that is the notion that the quantum mechanical world is represented by wave functions. And somehow the act of observing these wave functions collapses them into a definite measurable quantity. But that has problems. And so over the decades, it spawned a whole list of possible theories. This is a clip from one of the videos that I left in the links. And it's a really nice one. And he covers a lot of these different ways of looking at things. And he makes a good point, which I agree with totally, that the fact that we have so many possible interpretations to quantum mechanics is telling you that there must be some deeper theory of which these are all some kind of approximations to, that there has to be something more. And there's another wonderful channel, which I've linked to, which has great animations. And I'll come back to this channel later. And it's by Eugene, and I cannot pronounce the name. But again, he goes through in animation form the many different possible interpretations of quantum mechanics. And essentially all of these come about because entanglement generates paradoxes or contradictions that don't allow you to approach quantum mechanics in the normal way we're used to in classical mechanics. Now, to get a little bit of history, I think I wanted to go back before Schrodinger and look at how things actually came about. And that's also, I think, a very good approach to anyone who's interested in foundations of physics, is go back to not only primary sources, but go back before. Don't ask what Schrodinger did, but ask, well, what was Schrodinger looking at and thinking about that led him to propose his equations in the first place? And oftentimes that gives you insight into the physics that gets washed out in our textbooks. And I think, people have noticed this before, that when you read a textbook, you're getting the cleaned up result of the theory that's been put out there and debated and analyzed, but you never see where it came from. Where am I going? Oh, here we go. Could I share a different screen?
Yeah, you can share anything you want. You should, if you're on share screen, it should show, you should be able to find any one of your screens.
Meeting controls. I'm not sure.
Well, if you want to stop the share screen right now and then start, so stop share and then go back and share screen again.
Okay.
Now, if you share screen again, when it first comes up, you're going to see all the different things that are on your desktop, and then you can pick any any one of those that you want.
Okay, got it. So this is this is from Wikipedia. And look at the timeline. I find this fascinating. I would advise people that when you have time, because I know scrolling just drives your eyes nuts, look at the timeline for quantum mechanics. It essentially begins in the 1890s with experiments that start telling everybody that things are different, something else is going on. About this time, the late 1800s, beginning of the 19th, electronics starts to come in. We have transmitters, we have ways of generating vacuum tubes and electron beams. And so part of the explosion in quantum mechanics was technology at the turn of the last century started to allow a lot of these experiments to be able to happen because of electricity and electronics in its primitive form came about. So in the 1900s, you have Einstein with the photoelectric effect, special relativity, general relativity. The 19-teens, again, I'm not sure if it's coming through because I can't see here.
No, this is perfect, yeah.
A lot of the classic experiments that you read about in the textbooks happened in the 19-teens, but you have to remember World War I happened in this time frame, which really put a damper on stuff. And one of the sad aspects of this time in physics, if you read any biographies, is how many stories mention young, promising physics students in college leaving the university to go to war and never coming back home. So World War I did a really good purge. I mean, it really wiped out several years of graduate students who potentially could have gone on and been productive, but died in the war. That's a little sad thing. Then you get into the 1920s. This is when it really hits. Notice 1923, de Broglie proposes the wave-particle duality applying to electrons as well as waves. Then look at Schrodinger equation. Schrodinger took de Broglie's observation, and 26 is when we see the wave equation first appear. So wave equation kind of looks mysterious today, but it's the Hamiltonian from classical mechanics. And I tried sometimes to just put myself in Schrodinger's position as a young, physicist, trying to go, well, I have this thing now that is both wave and particle. And I have all my knowledge of classical mechanics and the methods that we use in the world of classical mechanics. Is there any way that I could modify something from the classical realm to make it work for this new object that has both particle and wave-like properties? And some physicists work by just total divine inspiration. They write it down. I suspect Schrodinger is more like the rest of us, that it turns into a kind of a trial and error. A lot of physicists are gifted with an amazing intuition. I think that allows them to guess ahead of time what might work. So the simplest thing you can come up with that has both a particle and wave-like properties is a wave function in the complex plane. Okay, so you've got that. Now, how do you fit that into the Hamiltonian formalism?
Well, would I derail you if I asked you what the Hamiltonian is?
No, and it's a good derailment because I was going to do it. Everyone, okay, this is an anal retentive trivial point. Everyone talks about Newton's equations, force equals mass times equation, acceleration. But classical mechanics, as we do it in physics, where it's done, so I don't do it anymore, is not based on Newton. It's based on something called the principle of least action. And I'm not going to go into it because there's lots of good videos on YouTube and explanations. But once that principle was discovered, it gave rise to a whole new area in classical mechanics. One of the first ones was Lagrangian formalism for classical mechanics. And then out of the Lagrangian came Hamiltonian or Hamilton's formulation of quantum mechanics. And you can take it even farther now, and you end up with a theoretical framework that involves these things called Poisson brackets, which look suspiciously like quantum mechanics, the Heisenberg formulation for quantum mechanics, which is actually what got me to grad school. As an undergrad, I was really fascinated by the crossovers between classical mechanics when you push the mathematical formalism to its limit and what classical quantum mechanics looks like. And I often wondered if there was a crossover. So I ended up in grad school to study classical mechanics. So I wanted to do the PhD in physics, but do my thesis in the math department. And at that time, Ralph Abraham was at UC Santa Cruz, and he was one of the main guys in classical mechanics. But then I get to Santa Cruz and he's not taking grad students anymore. So that's my sad story. Anyway, but back, I'm not sure that answers the question, because I don't want this to turn into.
So Hamiltonian arises out of Lagrangian formalism.
And that
and we can look it up. So
right, yeah, I don't want to be abrupt, but I don't want this to turn into a physics lecture.
Yes, yeah, exactly. So okay.
And the math is insane. This is the kind of stuff you don't get until your upper division physics major at best. So
okay. So now we have Schrodinger.
So right out of the box, because the Schrodinger wave equation is based on the principle of least action, we assume that principle is now going to be buried somewhere in quantum mechanics, and I'm not comfortable to go any farther on that one. But the point I'm getting at, since this comes out of classical mechanics, it brought everything with it from classical mechanics. And one of the things that it brought with it was this concept, or this phenomena of entanglement. And people all usually think of entanglement as presented as some kind of quantum mechanical weirdness, but it has a classical mechanics manifestation, and which we're all used to. So I want to unshare and get back to YouTube sharing.
Should be unshared. There you go. Okay.
Okay, and now I'll get back to. Which one? Nope, not that one. Not that one. What did I do with it?
That's what always happens to me too. If you want a second, I can put us on pause.
Hang on, here we go. I think I've got it.
Oh, okay.
Yeah. So can you see it now?
Yes,
Okay,
five little TikToks in a row.
Yeah, so I don't know, most people have probably seen this, but if you haven't, I'll start it at the beginning. And the metronomes are all going different. Imagine these are wave equations or quantum qubits, if you want. Now they all start out different, and you notice they're starting to get in line. And then I'll just quick go to the end, which is a couple minutes away. Now they're all going together. So that's a good example in classical world of entanglement. Each oscillator can sense what the other one is doing, because if you notice, the table underneath is shifting back and forth.
Mm-hmm.
So every time one of the metronomes goes back and forth, it makes the table go back and forth. So they entangle themselves because there is a connection. that's tying them together and lets each one sense the other. So that's one of the points that's always important to remember when you're dealing with entanglement, even at the quantum level. There still has to be something connecting the systems together. And you can even have fun. 32. I'll come back to this one later. But this one takes about 4 minutes. But this represents what you see in quantum computing later on. So this gives you an idea of what entanglement is. Now in our world, if you had put two metronomes on a hard flat table that had no connection, they won't synchronize up, they won't entangle. If you allow them to connect together, they will. Now in our world, if you take one of the metronomes after they've synced up and move it away and then bumped it, it wouldn't affect the other one. But in a sense, in the quantum mechanical world, that's what happens. It's as if one of the entangled partners somehow knows what happens to the other one. Now, this phenomena, which inherited into the quantum mechanical world from our world, it came with Schrodinger's equation. People knew it was there, but it wasn't until about 1935, when was it? Timeline. I'll look it up. 35 is when Einstein, Podolsky, and Rosen proposed the EPR paradox, which is what happens if you have two observers. The notion of if the observer collapses a wave function, and you start with an entangled pair, and they go out, the observer here collapses the wave function. Does that should affect or does affect what the other observer is going to measure? And that brings up problems. And it comes up in two ways. There's the issues of the observables, and there's the question of the observer. In physics, in quantum mechanics, there's certain observables that you can't measure at the same time. The Podolsky EPR paradox suggests that you can measure opposite variables at the same time. That leads to a violation of things like the Heisenberg uncertainty principle. But I don't want to go into the EPR paradox because it's subtle and it has a lot of variations on a theme. The various paradoxes, there must be dozens. I've never actually thought about counting them. And so I'll just leave it for people to investigate on their own. And at the same time, Schrodinger proposed the paradox of Schrodinger's cat. Now, this is a problem when entanglement affects the observer. And this is something that Chris Fields has talked about and other people have talked about, is if the observer is quantum mechanical system, then as soon as the observer tries to measure something that's quantum mechanical, the measurement entangles you. Like I say, the entanglement involves some kind of connection. Well, as soon as you try and measure something, if you're a quantum mechanical system, you are now entangled with what it is you're trying to measure. So the Schrodinger cat was meant as a criticism, I think, of the Copenhagen interpretation, because he was saying the cat in the box, you can't see it because of the way the experiment is set up. The atomic nucleus, which you were waiting to decay and send out the radioactive particle, which trips the Geiger counter, which releases the poison, that the wave function that describes that atomic nucleus is now entangled with the cat, because the cat is the observing measuring device. So the cat's wave function, if it's quantum mechanical, is entangled. So it can't measure. So in order for the cat to measure whether the atomic nucleus is decayed or not, you have to look at the cat. The observer has to now observe the cat. So it gets confusing when you start talking
Well,
like.
so the cat is in one sense the measurement device, but then an observer has to read the measurement device.
Right. So there has to be another observer to come in and look at the cat, open the lid of the box to measure the cat, because the cat's the quantum mechanical state. And the Copenhagen interpretation says it doesn't collapse down to a real quantity until an observer observes it. So you get into this funny thing where the cat's a superimposed entangled quantum state, which is both alive and dead. That seems to be now become the poster child for quantum mechanics, but it actually was meant as a criticism. But now you have a problem, and there's a link to it. It's called Wigner's friends paradox. So the observer that looks at Schrodinger's cat that decides whether the cat's alive or dead, now put that observer along with the cat in the box in a room and close the door. Now your observer is now entangled with the cat in the box. So now you have to have another observer open the door to see if the first observer has observed the cat. You can just keep playing this game. And this is what points to the fact that the observer can't be a quantum mechanical system, because if that's all the observer is, then it will become entangled with whatever it's trying to measure, which now implies that in order for the measurement to actually be observed, it has to be. I just better stop because this is making nonsense. But
No,
this
no,
is a
I mean,
problem.
Yeah, the observer cannot be on the quantum level, right? It has to be a level up from the quantum level.
Yeah, but what's the level up? No one has an answer or is prepared to give a good answer.
They don't want to talk about what the level up is.
Yeah, so that's hopefully the goal down the road, when we start to tie up this conversation down the road. So.
Well, I'm with you so far.
Okay, so
Yeah.
we're going to have to go in kind of waves, I think, on this one and approach different things. So I'm going to share my screen again. I'm going to talk about the delayed choice quantum eraser. Hopefully okay. Do you see it now? This is Matt O'Dowd from a PBS Spacetime channel, which
yes, I see.
I've always found to be a faithful source for physics. The thought that comes to mind is Peter Jackson's Lord of the Rings. It's a film adaptation. Everyone understands that it's not the book, but he was faithful in the archetypes. And so even if you're a fan of the books, you can still see his movies and be happy. But if you like the movies, it becomes an invitation to read the books. So that's how I look at PBS Space-Time. It's like, given the audience and the level, the medium that you have to work with, it's as good as it's going to get. And so I'm happy with that. And hopefully you'll take his videos as an invitation to go deeper. But this is one place where he doesn't quite get it, and he, I think, sends you off in the wrong direction. And I want to put a footnote in. It's all your fault, Karen, because I would have never cared about this stuff if you hadn't been asking me all these questions and I hadn't been trying to faithfully give you as good an answer that I know it would satisfy you. So you've pushed me deeper into a lot of these subjects than I would have ever gone on my own. And in the process, I've come up with stuff which is kind of amazed myself when I also apologize if these talks seem kind of disconnected. It's because this is the first time for me on a lot of this subject. So I'm struggling on finding words. But here's a screenshot from the PBS YouTube video describing the delay choice quantum eraser experiment. And I believe there's a link that I've given you if people actually want to go look at the paper. Now his description, and then to the right, I actually have the drawing from the paper itself. There's somewhat of a typo in the actual figure 2 here because it left out detector D4. Now, that's not a big issue. When you're dealing with experiments like this, you have to take a deep breath. And again, don't try and understand it. One of the images that comes to mind is like, some problems you can solve brute force mathematically. And there's some problems in physics, and probably the same as in life. It's like you have to sit and quietly wait for it to come to you. Like the primatologist Jane Goodall, when she first started studying the chimps and everything, she just sat out, went out to the forest and just sat there and watched and paid attention. And over time, the chimps got used to her being there, and they would maybe show her more of their behaviors, more comfortable. But it was a long, slow process of just being part of putting yourself into the experiment in this case, and watching and looking and seeing all the stuff that's not in the paper itself. This experiment is way richer than you would think just by listening to the quick YouTube demo. So what I do is I imagine I'm in the experiment. Imagine some kind of entanglement playground. Blow this up into this, it's a playground area. And the photons are kids that are coming in one at a time. And you're sitting on a bench down here somewhere in front. And there's a gate, those two little gates, the children come up one at a time. You can't see which gate they walk through. But once they pass through the gate, there's a magic crystal. It's silly, but it works for me. And there's a flash, and now there's a twin. There's the primary, and there's this virtual twin now. The twin wanders forward down your direction. These detectors are sitting in front of you. And the primary twin, the original one, wanders off to the far side of the playground where the interferometer in this case is set. Can you see the mouse on your screen?
Yes.
Okay. So I don't know if this works for people, but it works for me. So you're sitting there and just watching and paying attention. Now the detectors in the experiment are just simple photodetectors. They're capable of detecting a single photon at a time. But in the playground, I'll make them bells. They're a little bell with some kind of handle. And if one of the children bumps into it, it rings it. And that's what you're sitting there. You're watching the children come in, the magic twin go one way and the real twin go the other. And occasionally some of the twins will, the kids will ring the bell. Now, the first thing I noticed when I started paying attention to the PBS YouTube is he shows a screen and a double sit screen. And I'll look at the actual drawing of the description. There is no screen there. There's a single detector. So in the entanglement playground, there's no screen displaying what you normally experience as the textbook interference pattern. There's just a single bell on a stand, which is movable. Most of the primary kids that come into the playground and head off towards the far side, they never bump into the detector. They never bump into the bell. They never ring it. Most of the kids go into this experiment and never ring any bells, and they just wander off, and who knows where they go. That's an important question that is not dealt with in this experiment. What happens to all the photons that are not detected, which actually are most of them? The second thing that you'll notice is that while you're watching this, there's this magic, I don't know, a mysterious stranger sitting over in the far corner, quietly watching what's going on with a clipboard and paper and pencil. And that is our coincidence circuit, our coincidence detector. It's this observer sitting off in the side, listening for the bells. So most of the time, one of the kids will miss the bell entirely, won't ring it. Sometimes the virtual twin will come down, ring a bell, but the primary one won't. Sometimes the primary will ring, but the other ones don't ring. The only time this coincidence circuit detector, the mystery observer, makes a note is when he hears the primary bell ring and one of the secondary bells ring, roughly coincidental. At that point, all they do is they make a check on a box on a piece of paper that says, okay, bell D0 and bell 3 rang, or bell D0 and bell 4 rang. There's 4 check boxes, and that's all I do, puts a check. And so you just get these check boxes. So it's a busy experiment, there's lots happening, and virtually none of it is actually recorded except when there's a coincidence in time for one of the bells. Now this goes on for a while, and you're just watching. At some point, your mystery stranger gets up, walks over, and takes the movable bell on the far side, moves it over about a ½ inch, takes a tape measure out, measures it, writes that new distance down, and goes back, and then lets the experiment keep running. After a day, it's getting night, park's closing. By then, the far-sided bell, he's moved it over about 3 feet. And the experiment's done. We watch our mystery stranger close up shop. He tabulates all of the check boxes, enters those numbers in an Excel spreadsheet, puts it on a thumb drive. And the last thing we witnessed at that day, some poor grad student walks over to our mystery stranger, takes the thumb drive back to his lab, opens it up on a computer maybe, and looks at it. So now let's talk about it. No human has looked at this experiment this whole time. The first time any human observer actually looks at it is when the tech or the grad student looks at the data on the computer, which was basically an infinite amount of time quantum mechanically later. Second, this is a perfectly passive observer. No one's making choices, no one's erasing anything, no one's doing. What you see out of the experiment is what, in some sense, the photon twin pair decided to show you. So just kind of hang on to that. This is a very sparse experiment. And the other thing to think about is there's no time information. It didn't record phase. It didn't record intensities. So whatever you're talking about, diffraction patterns or interference patterns, we don't have any of that information. So when they present this as a double slit interference pattern, like you're used to seeing from your introductory physics class, that's not it, because that information is not collected during the experiment. And that's one of the big things which a lot of these YouTube, TED Talk kind of things completely leave off the table. And we'll see where that comes back later. So I need to take a deep breath. Are you still with me?
Yes, this one is a puzzlement to me because I've watched this one before, and then I watched the one that Sabina Hassenfelder did on why this one was wrong.
Okay, so we're going to get to that in a second.
Yeah. And so all of them, well, because I'm not a physicist, so I don't understand how they're measuring these things.
Right, so that's what
So in that way, the thing about the children in the playground makes it a little bit easier for me to follow.
hopefully I'm not sounding too crazy, but I think it's important. These are not simple experiments. They have stumped the most brilliant minds on the planet for decades. So don't think you're just going to get a YouTube picture of it and understand, because if you think you've understood it, then you probably haven't. And that's kind of what I want to push to a little bit farther. And I want to debunk Sabina's debunking. I really hate to do this because, anyway, I used to think she was a good person to listen to, but so we've gotten this far. Now I'll take the next step. Now this is from the actual paper itself. And I don't know if I'll just show this. Here's the paper, and you can pull it up. It's only 3 pages. 1, 2, 3. Okay.
Wow.
The 4th page is just references and diagrams. So there's no excuse for anybody not to have read this. And Sabina and Sean Carroll is another one. There's no excuse. Okay, can you see this one? It's got 3 diagrams and
Yes,
all right. Now this highlighted clip now, shows equations 1 and 2 from the paper. This is a correlation analysis. Remember, we didn't keep any information about phase or intensity. So there's no, whatever we're doing is not your standard interference patterns that you're talking about, analysis. Correlations in physics, they're important, but they generally involve products of wave functions, where interference involves sums of wave functions. So what the paper's doing is not your standard, it's not your grandparents' interference pattern. And the second equation, as soon as I saw it, okay, it doesn't mean anything to you, but you see those little A's, those are creation operators. And so that tells me, okay, we're in quantum electrodynamics world. This is, this is graduate level quantum field theory stuff. So this is a very sophisticated analysis, theoretical analysis, not something you just want to walk into and wave your hands and say it's all. The supposed wavy patterns you see, those come out of correlation functions. And so the lines represent the theoretical predictions from all of this stuff, the mathematical analysis. And because you're in the realm of quantum electrodynamics, it turns out there's a 180-degree phase shift, or a pi radian phase shift between the 2 correlation patterns. So that's what you're seeing in these 2 drawings. If you add them together, of course, you're going to see the normal undiffracted, uncorrelated pattern. But then, of course, it's not surprising to me that you see this, because that's all you were doing to begin with, is just counting coincidences when the different bells rang. You weren't keeping track of any phase or anything else information. So I'm happy with this analysis. I don't say that I understand it. I am not prepared to dive into it and explain it. Quantum electrodynamics is a world away. It's like 30 years back. I'm not going to tackle it again. But it's a sophisticated analysis, which the YouTube approach doesn't answer. So now I can unshare, I think, for now. What's the next one? Okay, so Sabina supposedly did a debunking, but if you listen to her analysis, it's like she's debunking Matt's PBS space-time video. Again, she puts up the same picture that shows a diffraction screen with the diffraction patterns. Nothing in her analysis told me that she's paying attention to the actual details of the experiment. The screen thing is big for me because in the actual experiment, it's a single detector and it's moved. That detector sits there for a while, then they move it over, then they take samples for a while, they move it over. You would think she would have acknowledged that. Her analysis is more interference-based. Nothing in what she does in her video tells me that she's actually read the study and addressed the actual analysis, theoretical analysis in there. So I was just
so here's a question. In her video, she showed that while it looks as though on D3 and D4 that there is an interference pattern on each of them, if you put the two interference patterns together, they're off phase sort of. And so
right.
if you put them together, then it's just it's the same blob in the middle, and it's not an interference pattern. When you just showed those three graphs, the way you explained those three graphs was that the two graphs, when you add them together, you get the curve. So is that the same thing, or is that a different thing?
Well, what I'm saying is, of course you are, because that's all you've ever collected. You know, your little mysterious stranger, you know, the coincidence guy. He just counted things. The data that was collected has nothing to do with interference patterns. It's just coincidence detections between one detector and another. The squiggles, the lines that you see are not an interference pattern. They're coherence values from analysis based on coherence.
Okay.
And I'm not going to tackle. I'm not going to try the
that's
math.
fine. But so there is a differentiation there.
The analysis that is actually done in the paper is not what Sabina is talking about. Is what I'm trying to say.
Okay.
And I'm disappointed. It's a 3-page paper. She's a theoretical physicist. She knows her stuff. And okay, simplify it for the sake of a YouTube video, but at least acknowledge somewhere in there that you've paid attention to what was actually done. So no, they're not interference patterns in the sense that you learned it in introductory physics. Now, what's even worse is Sean Carroll, that he apparently did a debunking, and I listed that. Both of these are in the list of links I gave you. His debunking takes place in a blog post, and he doesn't even address the experiment at all. He comes up with a parallel experiment based on spin 1/2 particles, analyzes that, and then debunks that experiment. And I'm thinking, Sean, you didn't even talk about the experiment. You just, I'm sorry.
Well, I wonder how much of this goes on in science all the time, where people, we've been watching Dope Sick, which is really horrendous. Just the saddest thing. It's the actual story of how Purdue Pharma introduced OxyContin and told everybody that it was not addictive, and really pushed that with the doctors so that the doctors would push OxyContin, and created the whole opioid crisis in our country. And when it finally got to court, it turned out that the study that they were using to prove that it was not addictive was not a study at all, but that supposed study had been listed in every single major news media, in all of these scientific journals, cited as a study. It turned out it was actually a letter to the editor in in a journal like 30 years before. And they brought that guy who wrote that letter to the editor into the court, and they asked him, do you know that this letter has been used in these ways? And he said, no, I didn't know anything about it. He said, I just wrote that letter based off of some calculations that I made on the back of an envelope. And I wonder how much of that stuff goes on all the time.
A lot, now that social media has become dominant. I'll just say my piece and get on this, my opinion, that a year, 2 years ago, I did, without hesitation, recommend Sabine Hassenfelder as a go-to physics source. This last year or so, she's really actively monetizing her channel. I think she's probably gotten on that YouTube treadmill where you monetize and then you have this need, you have to keep generating content. And so I'll be gracious and just say that I feel like she's for the sake of constantly generating new content, she is going into areas that she's neither prepared to or have the background to discuss. And so she's making rookie mistakes. But sadly, I don't feel comfortable telling people to listen to her anymore. I think she's crossed a boundary for me, and I don't want to go there. As far as Sean Carroll, I've never kind of liked him.
Mm-hmm.
I kind of feel he's the Sam Harris of physics world.
Exactly right.
But in a more professional criticism, this delayed choice with quantum eraser experiment, this is one of the biggies. This is a landmark experiment. And if you as a physicist feel that you have a legitimate criticism of the analysis that was done for this experiment, you have a moral obligation in the Nima Harkani Hamed sense of publishing your analysis in a peer-reviewed journal and getting it out there. Because if you can find a legitimate flaw in the analysis behind this experiment, that would be huge. That would be a major milestone in physics and understanding of quantum mechanics. The fact that neither of these two prominent physics people have done that bothers me. It's not right. They need to put it open for discussion, not go to a blog post or social media. Anyway, I've had my say.
Okay, we're done with our soapbox now. So we're back at the actual reading of that experiment. So what were the implications of it?
But the Sabina and the Sean Carroll thing, it does open a door for something that, the little side thing I didn't post a link for, but it came up, I think, maybe tangentially with another conversation that you talked about Pierre Duhem, his name has come up. Mm-hmm. Besides To Save the Phenomena, he also wrote another book called The Aim and Structure of Physical Theory. And it turns out Duhem, along with Karl Popper and Thomas Kuhn, are three big names in the area of philosophy of science. You know, Karl Popper is famous for his falsification hypothesis. The thing that Duhem brought to the table is the notion of hypothesis testing. And he made a clear point that when you do experiments like this, you're not just testing one hypothesis. You know, you have an hypothesis about how a single slit versus a two slit diffraction, how do the special doped crystal work that creates the entangled pair. There's a whole physics behind the Glen Thompson prism, beam splitter prism. There's a whole physics behind how the semiconductor photodetectors work. So there's not just one hypothesis, there's a whole host of hypotheses that all underlie this experiment that you're doing. Sub-assumptions, I guess you'd call them. So now there's got to be dozens of these experiments dealing with entanglement and observer and observables. They all will share certain commonalities in terms of detectors and slits, and so each test of quantum mechanics and is like a Venn diagram. Each has their own Venn diagram, and there'll be intersections of sub-hypotheses which show up in all of these. So if someone like is going to criticize this experiment, in some sense, they're criticizing all of the experiments of like type. It's kind of a more holistic view of things. And the flip side of this is that whatever explanation you're going to come up for that explains what you see in the various experiments also better be applicable to all the other experiments at the same time. So when you, and this is the hard part for me, is so when you're dealing with this quantum eraser observable stuff, it's a big thing you're carrying along. It's everything you have to answer, everything you criticize. And again, I find fault with Sabina in her YouTube videos that she doesn't offer explanations that will now apply to other things. And she doesn't do the Peter Jackson Lord of the Rings thing, which a good video should, I would say, edify, explain, and encourage you to dive deeper. And so her YouTube video debunking doesn't do any of those. It doesn't explain, and it doesn't encourage you to go, it's not an encouragement to go farther. And it doesn't offer explanations for others. So that's kind of a burden, I think, that a physicist brings to this discussion. You need to think in a very holistic manner when you're tackling this. And so if anyone wants to dive into this, the Duhem-Quine hypothesis, it's out there.
That's really interesting. And before we leave that topic, I also want to put in a plug for Paul Feyerabend.
Okay, cool.
I've been reading this, and he has a lot in here about the whole philosophy of the areas in which science has sort of gone off the rails. And there's just really a lot of good stuff in there.
Mm-hmm.
Yeah.
So doesn't that connect back to Gregory Chaitin's? Wasn't his wife into?
Yes, that's how I got onto Feyerabend, is because Virginia Chaitin was talking about how she was helping to host a Feyerabend conference or something. And I thought, well, who is this guy? So I bought the book and I started reading it. And I go, oh, wow. Yeah. Like every page is chock full of things. I've got notes scribbled all over it.
Yeah, so that's one of the cautions. If you wander into the field of philosophy of science, it's a rich field that's people have been in it for decades, generations, and huge minds. And so don't think you're just going to go out there and understand stuff immediately. So, okay.
No,
we're going to stop
that's why I take it one page at a time.
Okay, we're going to put delayed choice with quantum eraser on hold for a little bit. And we're going to visit this thing called the strong free will theorem. And thankfully, where is it? I can't explain it. The math is crazy. I think I left a link to the papers. It's two papers that have come out in the last 20 years. One was the free will theorem with Simon Koshin, physicist, and the mathematician John Conway of Game of Life fame. And also, I think you've had a recent discussion of John Conway and the Monster Group.
Oh, yeah.
So yeah, Conway seems to come up in funny places. It seems mathematically, but thankfully I ran across an animation that shows you the essence of the strong free will theorem. And I will find it here someplace. (1870) 2240. So I'll share screen and I will let it run for you. Can you see it now?
I can.
Okay.
These types of instantaneous messages, which are faster even than the speed of light, then this creates an interesting situation with Einstein.
Okay, yeah, this is good.
According to Einstein's theory of relativity, different observers will disagree about which of two events happened first, and no observer is more correct than any other. From one observer's point of view, the right particle was observed first and caused the left particle to change its spin. From another observer's point of view, the left particle was observed first and caused the right particle to change its spin. Therefore, we can't know which of these events is the cause and which of these is the effect, since both points of view are equally valid. In fact, according to quantum mechanics, we can't even know which particle is which. Suppose.
Okay, I will stop there.
Well, there we are, right stuck in the postmodern conundrum.
Well, what Simon, Koshin and Conway did was they took Bell's experiment where you have two observers, Alice and Bob, each independently making their choice of experiments or measurements to make on an entangled quantum system. So you get this notion that Alice makes her measurement before Bob. If you accept the Copenhagen interpretation, she collapses the wave function for both of them. So that should affect now what Bob is going to measure, even though his choice of experiments might have been completely different than what Alice chose to do. So that's essentially Bell's experiment, Bell's theorem, was that he came up with a clever experiment that took the entangled pair, and by the choice of experiments that each one chose, you let them do this over and over and over again, and you accumulate some statistics, and then you look at the correlation between the results that Bob gets with the results Alice gets. And if you assume that there are, well, one of the ways out of the EPR paradox, which is always was kind of implicitly assumed, I think, by a lot of people, was that quantum mechanics was not a complete theory, that there are things going on in the quantum mechanics world that we as classic observers will never have access to. So it might seem a mystery to us, but that doesn't mean that at the quantum mechanical level, hidden from us forever and always, there isn't variables and explanations that make perfect sense. So that's the notion of hidden variable theory, that there's stuff out there we can't access, never can, but if we actually knew it, maybe we could explain what's going on. Bell's was originally a thought experiment that said, well, if you could run this clever test and do the statistics, it will tell you whether there are hidden variables or not. It would force hidden variables to show their hand if you do the experiment. Well, come with the 1980s, they were finally able to do John Bell's thought experiment in the lab. And sure enough, Bell was correct in the sense that there are no hidden variables. And now you're stuck with, okay, now what do we do? Does her measurement affect Bob's? Does Bob affect Alice? What's happening is there, and this is where you get into the retrocausality. Does the future affect the past? That was one of the explanations. So I think that's one of the alternate explanations for quantum mechanics is retrocausality, the fact that future can affect what's happened in the past. So measurements in the future, what Kochen and Conway did was they say, if you throw special relativity into this, you can find inertial frame or Alice is first. You can find an inertial reference frame for Alice. Bob is first. So this whole notion of who goes first kind of goes out the window, at which point the whole question about past and future in an experiment kind of gets fuzzy as well. So now we're here. Now that we've kind of thought this way, let's go back to our playground. You were sitting there as a stationary observer on a park bench watching this experiment. In your experiment, the bell that the primary child rang was way closer to the gate than the bells that the virtual magic twin would ring, much farther away. But if you can get into a relativistic Mini Cooper, like in the animation, and drive by this park, the entanglement playground, you could find an inertial frame in which the magic twin rings the bell before the primary child rings its bell. So this whole notion of before and after gets swapped out, maybe. Not always. Some experiments, this won't work. There's, like I say, there's dozens of these experiments, and we'll look at another one. But in this particular case, it looks like the strong free will theorem throws a real monkey wrench into this one. So now you're stuck. I'm not sure what you want to do.
Well, so what is the strong free will theorem is saying exactly what about free will?
Okay. It raises the question, if Bob or Alice, they have free choice, okay, to decide whatever experiment they want to do. And free choice, we're going to get to that next. We're going to come back to that. But that says their choice is not determined by the past history of the universe. So I'm going to try and share again, I think. Now, these next few screenshots come from a YouTube channel called Cracking the Nutshell. And the host, her name was Dolores, she's gone quiet for the last few years, but thankfully her videos are still posted. And this came from one called Do Electrons Have Free Will? And she analyzes she does a very good analysis, I think the best of anything on YouTube I've seen, of the free will theorem. And this is one of her slides. Free choice in physics is simply a choice not determined by prior conditions, the past history of the universe in any frame. It's not free will. I kind of look at it. Free choice is how the Mother Nature, how the universe sees things. Free will is how we as conscious living beings experience this property of free choice. It's not the same thing, they're related. So he's not proving, the Conway quotient doesn't mean that the electron has free will. But what he's saying is if the observers, Alice and Bob, have free choice in selecting the experiments of the menu items they have randomly to experiments to do, then the electron must have free choice as well. Now, this always confused me. How do I explain this to somebody? And the concept of free choice brings a lot of baggage with it because you think free will, and it doesn't capture exactly in a mathematical sense what's happening. If the origins of life questions or consciousness, intelligence, all these kind of philosophical questions are going to become physics questions, and math is the language of physics, then you have to put these kind of questions into mathematically rigorous terms. So I asked myself, well, how would I put this notion of free choice into a mathematically rigorous statement? And I think this is probably the most useful thing, is it's the notion of causal independence or causal decoupling, that the chain of causation is broken. So when we say universe has free choice, we're saying that strict determinism is broken. The past history of the universe does not uniquely determine what the next step is going to happen. So I thought that that might be a good handle. Stop maybe using free choice because it's a little bit loaded, but just say causally disconnected, causally independent. I don't know, does that help work for you?
Yes.
So each one of the observers in the experiment has free choice. Their choice of experiments is not predetermined. So however Alice and Bob as entities act, I mean, we say they have choice, but they're actual physical entities acting on something. So however actions they're doing is not disconnected. You can't predict with absolute certainty what they're going to do, even if you knew the total past history of the universe. That's a very strong statement in physics, which a lot of people don't want to make. So I think we'll come back to that second. Now, while we're here, I want to drop back to, there's another delayed choice quantum eraser experiment, which is much more related to.
Oh, this looks like the bomb experiment.
Yeah. It's John Wheeler and Baum. I think this is their experiment. Now, this one's, again, it's a different take. It's a different way of setting things up. It still has detectors. It still has beam splitter mirrors, half silvered. But in this case, the observer is actually actively taking part into the experiment. I tried to find a good video, a good drawing for display. I couldn't. So these are pictures from the paper itself. So this is a schematic. A single photon comes in. There's the beam splitter. The photon can go either path 1 or path 2. And then up here at the detector end, there's a beam splitter or half silvered mirror. Now the photon will come in, possibly take both paths, maybe, but if we just leave the experiment as it, we will see a interference pattern as we, imagine the two long strides are like the trombone slides. So as the experiment slides back and forth, and as we move it and we make the lengths longer, you'll see an interference fringes come and go at the detectors. And what happens is these half silver mirrors, like in the other experiment, they confuse you. You lose path information because of the half silvered mirrors. But if we take this half silvered mirror out, so that path 1 goes to detector on the top and path 2 only goes to detector on the side, then you will count photons. You will see, you will lose the which, you'll know which way the photon went because of which detector clicks, and you lose the pattern. So they came up with a clever experiment that can take the beam splitter out after the single photon has passed through the first half silvered mirror and is already on path 1 and 2. And they do this, they're using a random number generator that is triggered by the first photon coming into the experiment. So once the single photon has come in, it's taken path A or path B, or who knows, both at the same time. The configuration of the experiment is switched in a random way. And then you look at how the experiment happens and you work it out. You know, you get the you get the double slit diffraction, you get the normal diffraction pattern if the beam splitter is a certain, I'm sorry,
That's okay. This is really complicated stuff, and
it's complicated, and my mouth is getting faster than my brain.
so on this one, it says here it's an experimental realization of Wheeler's Gedanken experiment.
Mm-hmm.
I hadn't heard about that one. Is
Right.
that John Wheeler?
It's John Wheeler, yeah.
Oh, I hadn't realized he was involved in this kind of stuff. I thought
Yeah, all the big
mainly
names were.
I thought he was mainly a computer guy.
No, you're thinking maybe von Neumann. But the difference I want to point out in this one versus the other delayed choice quantum eraser is the first one is completely passive. In this one, there is an active element that during the middle of the experiment, after the photon that came in has already made its choice as which path to take, you actually switch the experiment up actively and change the output detector configuration after the photon has already entered it. And it's done by, so if you're thinking of free choice in the strong free will theorem sense, that the observer, Alice or Bob, had free choice to decide what experiment to do after the experiment was already started. In this sense, the random number generator has replaced Alice or Bob. And so to say, you know, to take free will and turn it into a mathematical concept that you can actually work now theoretically. What I'm trying to say is, to say that a true random number generator exists is the same as saying that free choice in physics exists. And that's what this experiment's trying to tell you, I think, one of the important things. And it's a way to get from the free choice to a more mathematical description. So that is a question, do true random number generators exist in this universe? Because that's an example of an output, an outcome, which is absolutely unpredictable from the past history of the universe.
Because the input is coming from this random random number generator. But then it's going through this little beam splitter output that is unknowable before it happens, which path it's going to take. So
this happens in the space of nanoseconds. No human can step in there and make decisions on that time scale. So the random number generator has replaced Alice and Bob in deciding what experiment to do on the output after the photon has already come through the input gate scenario. So whatever you say about Alice and Bob is of having free choice or not, you have to say about the random number generator.
So then the implications of this is that free choice is not just
free choice is a bit loaded, but I'm trying to just say
causally independent.
Causally independent, causally disconnected, causally.
So is the I'm sorry, this is really a stupid question, but is the idea that photons are causally independent? That they're somehow making.
Well, I think that's probably a less loaded way to determine or to interpret John Conway's choice of strong, free will theorem. Is that he's saying if Alice and Bob are causally decoupled. Their choice of experiments is causally decoupled from the past history of the universe. Then the outcome of the experiment, what the electron or the photon decides to do, is also causally decoupled from the past history of the universe as well.
Well, I mean, I noticed you used the word decides.
I know I'm trying to offer a way to phrase this so it's not so.
Well, you know, one of the things that occurred to me from watching, I've watched several videos all in a row lately. One of them was the one you sent me with Chris Fields and Michael Levin and Mark and Carl Friston. And another one was one with Sabina Hassenfelder and Paul Davies and Lee Smolin. And I thought that Davies and Hassenfelder didn't have much to add, but Lee Smolin was very, very interesting. But in watching these things, I keep coming to the conclusion that there has to be some sense in which these decisions are made at these very low levels. So one of the conversations I had recently with Michael Claridge, he was talking about, and I'm assuming he knows what he's talking about, that a photon that goes from one end of the room to the other goes every possible path in the room before it gets to the other side, which means that in some sense, that photon, if you could ask questions of it, if you could connect up bits, you know, John Wheeler's bit, the yes or no question, you could ask yes or no questions about parts of the room, and that photon would know because it's been there. It has experience of every part of the room before it gets to the other side. The way it sort of mapped out in my head is that the photon actually must have some kind of a, I know there's probably no storage inside a photon, but if there were, there would be a map in that storage of the room, of every obstacle in the room that the photon couldn't go through and it had to go around in order to get where it was going. So there would be a 3D map of the room inside that photon, which sort of says to me that everything in the universe is somehow known by every part of the universe. I know that's really a weird place that my mind has been going lately. But then when I hear Fields and Friston and Levin talking about how biology and psychology and philosophy and physics are really the same science, they're really the same thing. That's what I've been trying to say for a long time, is that there are certain principles that are meta above all of these laws. There's principles that are above all of these specific small laws. And if you'll just give me one more second, I want to read this quote from Lee Smolin. He said, when we talk about these laws, we're actually talking about laws that govern small parts of the universe. They're local. But what kind of law selects those local laws that govern the small regions? What kind of law governs the cosmological questions? There's, to me, that law, that set of laws or law is actually a set of principles, not a set of little minute regulations or governing equations, where so many physicists want to talk only in terms of the differential equations and all the mathematics and everything. There is something a level up.
Okay, well, we're headed there.
I have about 15 minutes. So can we maybe break this up into 2 episodes?
Oh, we'll have to.
Yeah, because there's no way 15 minutes is going to wrap this up.
Okay.
Yeah, so let's see where we can go in the next 15 minutes.
All right. Well, now that we sort of talked about this concept of free choice, and that maybe a better way to encapsulate it or talk about it is to talk about causally disconnected. that things can happen in the universe now which are not predictable ahead of time. And that's actually, I think, a very strong statement. A lot of physicists might run away from it. But the only alternative to that is what they call superdeterminism, which basically says we live in the matrix. And so pick your poison, and we'll come back to that. Now I want to again come back and take another pathway and look at quantum computing. And the whole notion of qubits. We have the idea of observer collapsing the wave function. And so right off, you kind of go, okay, well, does quantum computers actually compute? Because you don't really know the answer until an observer looks at the computer and collapses the wave function. And now you have a real number or result that you could measure. And that's one of the challenges unspoken of quantum computers, is that even though in some sense theoretically they're solving all the possible cases at once you measure it, you only get one answer. But there's another half that people are neglecting to the quantum computer. In order to get a quantum computer to compute, you've got to program it. How do you program a quantum computer? No one ever talks about this. You have to set up an entangled state, right? You don't just turn the computer on and let it run and you get an answer. You have to program it. You have to forcibly entangle your array of qubits in a specific way, and then let the system, and then step back and then let the quantum computer do its time evolution. And at some point later, you have to stop it by observing it. Well, so I'm going to share this screen. They actually do have working quantum computers. And I think one is up in your neighborhood at NASA Ames. And I believe Google has got source, have been using it. But imagine all these metronomes now are qubits. And so to program a quantum computer, there has to be a compiler of some sort, which is going to take your algorithm and turn it into a matrix of entanglements. And then you have to somehow go in and manipulate all of the qubits and set them up in the right entangled way so that you that's how you encode your problem into the system. And then once everything's entangled, there still has to be some kind of connection between the two so that they know about each other and the whole entangled state can evolve. So this is the quantum computer programming. So we're manipulating qubits, and now we're letting it run. And sometime in the future, we stop it and we read. Now, hopefully kind of share that image. I think I haven't looked for a while, but I think there's at least 6 or 8 or a dozen different ways you can create qubits. In the raw technology of silicon and all this, there's multiple ways to do this. And of course, depending on the qubit you're working with, there's different ways to massage it into a specific entangled state. But what's doing this? You know, if the observer collapses the wave function and freezes it, we've got this actor, which is basically the mirror or opposite of the observer. It's acting on the quantum system, deliberately setting it up in entangled ways. So there's, I don't know, I thought maybe the actor, call it the actor, that's going from the classical world, you know, where you have algorithms written on pieces of paper, and you know, if they're magnetic regions, you manipulate them the same way you do in nuclear magnetic resonance that the chemistry labs use. It's standard techniques. But isn't that a quantum weirdness as well? So I thought actor, and then I thought, well, it's an effect. People like to use the word affect. So it's the affector is the opposite of the observer. So you imagine the quantum computer is the programmer stage and the readout stage. The affector sounds like a supervillain. I don't know. So someone's got a better word, but it's the complement to the observer. And I've noticed, since you've pushed me to think about this stuff, no one ever talks about this aspect of the observer. So what if you take the observer and the effector and concepts and push them around and put them together like this? The observer and the effector. And it's sort of like, the Janus God. Now let's take this notion that it's actually a composite. We've always physics spent forever thinking about the observer, totally neglecting the effector side, to put them together as one object and try and think about things as one composite object, as one thing. Now go back to our entanglement playground. Our virtual, our magic child comes up and rings the bell. The observation isn't just the bell, it's an effect. So the act of observation of the photon detector creates an effect, which is the sound of the bell, which travels to the, our mystery stranger coincidence detector guy. So an observation is something, it's one of the aspects, is that it generates or creates this causal chain now of things happening. If we think about all of the children who walked into the park, wandered off into the forest, whoever knows, they never were observed again, but because they never generated an effect again. So one of the things that distinguishes what the observer does is that it also creates an effect back on the universe at the same time, which creates this chain of events now that eventually ends up as a record on an Excel spreadsheet in some grad student's computer. All of the stuff that went into the experiment that never, it was all the photons that go in there get absorbed somewhere in the walls of the box that this whole experiment's in. But because they never create an effect that goes out, that we as classic observers, we're an observer too, experience, it doesn't have an effect on the experiment. So things for me are getting a little bit fuzzy. I'm not sure. I feel like I'm witnessing a magic act. I'm uncomfortable, but I think it's something unique to think about that the physics community doesn't talk about, is that the observer is actually a composite object, and we better look at it as observer effector, that the observer by itself doesn't do anything. And well, here's a funny take.
Is it I'm just trying to clarify here. Are you saying that the observer is a composite object made up of observer and effector, or are you saying that the observer has an effect that is not typically recognized, and so the observer is an effector in a way that is not typically recognized?
Yeah, it's just in terms of theory and how people look at problems, that the observer is just one half of a single object, and we spend our time looking at the observer side and have neglected the effector side. But it's really one object, and we better start thinking about it as a single object. In some of the multiverse theoretical concepts where there's different laws of physics in all these different universes, there's a funny question, well, is it possible that there's universes out there that don't have observers? And then, so you get the notion of a zombie universe is one that doesn't have observers. So I'm going to borrow terminology and say a zombie observer in this context is one that doesn't create an effect afterwards. The quantum particle comes in, it becomes entangled with the observer wave function. Nothing happens. It's called quantum decoherence. It's a process. It's studied. The photon comes in, the detector entangles together, nothing happens. In that case, no observation actually happened. We don't know an observation happened unless there's an effect that ripples out the other side. So,
Well, I think what's coming up, and so maybe this is a good place to end for today. I don't know if you got a chance to watch John Vervaeke, Jonathan Peugeot, and Jordan Peterson in discussion a couple of days ago.
no, I have not yet.
It's remarkable in this that he's starting out with a very simple sentence, and then they start looking at, well, could this be true in all particulars? And then it just goes out from there, because one simple little statement has so many aspects to it that it never ends. And I think what you've stumbled on here is that this is exactly the same way in a physics experiment, because there's not only all of the previous shoulders of giants that you're standing on to put the experiment together, and all of the implications of all of their work is in this one little box, but then there's all of the ramifications that expand out from it in terms of all the implications, and it just becomes combinatorially explosive. And so you're starting now to dissect this one experiment and think about the implications of it in ways that I think are really important. So I do want to continue this, but I'm going to have to.
Okay. Well, it'd be good to get some feedback on this one if you want to publish it first. But it seems like everything's going to blow up. But I think you're going to be amazed how fast it all collapses back and gives a wonderful answer to a lot of questions.
You mean when we get into episode 2?
Right.
Yeah. Well, we certainly laid some groundwork here, and you've given people plenty of homework to do in the meantime, because we do need to look at some of these videos and study Wigner's friends and the Einstein-Podolsky-Rosen paradox and the whole timeline of quantum physics. And yeah, we have plenty of homework to do. It's been so great to get back together again with you, Glenn.
I know, it's been a while.
Yeah, I can't wait until next time. So we'll catch up with each other by email and figure out a time.
Okay, well, thanks a lot.
Okay, good talking to you.
Bye.